last class we saw that under certain conditions, certain situations, the inductive element or inertial element will need to be represented with two bonds. When that will happen when the effort variable that is created from the history of flow, that is dependent on the history of flow in two different places. That we have seen happens in case of mutual inductance, and where we considered this circuit, and we decided that the momentum here and the flows are related by this kind of a matrix equation. So, under that condition it would be necessary to represent it not as this, but as this. Okay. So, that is the point to which we went in the last class. It is easy to visualize this in the electrical circuit, but can we think of a mechanical situation that will necessitate the use of two port I element or I field? Such a situation actually arises when, for example, let me give an example. If you have a mass here that is connected to another a spring and to another mass, say that is connected to another spring to ground. Do not argue how it will stand, because it may be by means of some kind of a guide that is made to stand like this. Okay. We are considering the up and down motion, but in that case we have to find out, we have to specify what we call as the datum from which this mass, its position is measured, and also the datum from which this is measured. Okay. Now, you might say that okay, let this be the datum from which this and that both are measured, or you could say that I would say this is my say Q1 and this is my Q2. That is also possible. You would notice that if you do that, then it would be necessary to represent it by means of a I field. Let us see. If you have this, then the way we did it in the last class, for this one we wrote the kinetic energy equation, and from there we obtained the momenta. Let us see what would be the kinetic energy of this setup. The T would be half m1, this is m1 and this is m2, m1 times what square? Now, its motion will be, will be dependent on both. So, q1 dot plus q2 dot, q1 dot plus q2 dot, this fellow's square plus its kinetic energy, which is half m2 q2 dot square, q underscore, sorry, q underscore. So, in that case your P1, which is the derivative of the kinetic energy with respect to q1 dot, will be, do that, what do you have? M1 q1 dot plus q2 dot plus m2 q1 dot. Similarly, P2 will be it will be, yes, fine, which means again the P1 P2 as a vector becomes related by some kind of a matrix to the two flows. These are the flows, right. So, what is the matrix? No, P1 M1 plus M2 M1, yes, fine. So, this is after all related by a matrix equation, and therefore, in order to represent this you would similarly need a 2 port I element, an I field, right. When would there be a C field similarly? Well, capacitances are never coupled, so we would not directly consider, since we consider the capacitances as isolated elements. So, it is in electrical sense an electrical capacitor will be an electrical capacitor's governing equation is I is equal to C dV dt, or V is equal to integral I dt. Okay. So, the history of the current determines the present voltage. Now, this is normally in a capacitor, its current determines its voltage. Can you figure out a situation where somebody else's current will determine its voltage? No, not in a normal capacitor, not in a normal capacitor, but there can be cross coupled capacitances where there are various lines and in between there are capacitances. So, these kind of situations, relatively complicated situations, would need this representation, but let us leave that for now. In mechanical system, for example, there are beams, and wherever there is a question of beam bending, that is something like a capacitance, and that can be dependent on the motion in this part, that part, they can be related. So, the beam bending problems often result in cross coupled capacitances, but let us leave those complications for now. But in those cases, remember, you would need a C element with a 2 ports C field. When can you think of having a R field? Wherever the voltage and the current, what is the relationship between the voltage and current in a R element? V is equal to IR, simple. So, the effort is equal to the constant times the flow, that is right. So, if you find a situation where the effort in 2 bonds are related by some kind of a matrix to the flows in 2 bonds, or the flows in 2 bonds is related to some kind of matrix to a effort in 2 bonds, then obviously you need an R type of element. The such kind of situations very often occur, for example, in electronics. If you have, say, this kind of a situation, if there are how many voltages, say here is a current, here is a current, here is a voltage, here is a voltage, how are they related? You notice immediately that they are related by that kind of a relation. So, whenever a circuit contains a, say, any of these devices, then you would need a R element. But presently we are considering, in this course, we are considering mainly electrical circuits, mechanical systems and electromechanical systems. So, we understand this will occur, but let us not concern ourselves with this right now. If they occur, we will take them. But we need to understand how to obtain the differential equations for this kind of a system. So, let us take that up. Its bond graph we had concluded would be like that. So, let us power direct it. It would be this, fine. So, the power directions are done. You have the causalities now. SE will be receiving flow and giving effort, C will be receiving flow and giving effort, I will be giving flows. The moment the flow comes here one junction, it has to distribute. So, this is done. The moment the flow comes to this one junction, it will distribute. So, this is done. So, it has received the flow from both the directions, it has taken out effort in two directions, and therefore, this bond must bring in the effort information, which is like this. Done. So, you have causal it, and I will now assign the numbers 1, 2, 3, 4, 5 and 6 and 7. Okay. Fine. Now, let us start asking the question with relationship to all these elements. Let us start. Shall we display it like this? Can you see? Fine. So, let us display it like this and then write it here. First, we ask the question with respect to the SE. What does it give to the system? It gives E3, which is the externally applied voltage E. Next, we ask this question to this C. What does it give? So, it gives E7. E7 is equal to Q7 by C, right. Then ask this question to this inductive element, which is now 2 port. In this particular bond, what does it give? F1, no F1. So, F1 is equal to what? As yet we do not know that, but we will soon know. But in this bond, what does it give? F2. So, we will need to know F2 also. Now, we have seen this is F1, this is F2. This is F1 and this is F2, and they are related by this relationship to the momenta. So, let me substitute this as F1, this is F2, and then can we extract this F1 and F2 from here? Yes, we can. Essentially 2 equations, 2 unknowns. Just obtain F1 and F2 individually from these 2 equations. Do it. What? Oops, sorry, yeah, it was here. Sorry, it was here. So, these 2 are, I'll just, these 2 are actually F1, F2. So, from here can we find out F1 and F2 individually? It will turn out to be L2 P1 minus M P2 by L1 L2 minus M square. Let us check that. F2 will turn out to be M P1 minus L1 P2 divided by M square minus L1 L2. So, these 2 can be obtained from the original equation. Let me write down the original equation so that you can feel comfortable with it. what we said was here the relationship is P1 P2 would be times F1 F2. Normally the momentum is the mass times the flow, but here the momenta in the two bonds would be related to the flows in two bonds by this relation. So, from here we obtain F1 and F2. Clear? Now, in addition to that, we will need to know, is it visible? Yes. We will need to know the what does R give to the system. What does it give? No, it gives E. F comes this direction, E goes that direction. What does it give to the system? E, E5. So, comma E5 is equal to R times F5. So, first we relate to the character of the system and then we find where does F5 come from. So, F5, where does it come from? Sorry, I have not given the power direction here. Yes. So, where does this come from? F4 minus F6. So, no, F4 minus F6 is equal to F5. So, R F4 minus F6. Now, F4 is what? It is a F1, because it is a one junction where the flow has come here. So, this is the strong bond bringing in the flow information F1. So, this is equal to R F1 minus F6 is what? Again 2, F2. So, subtract these two, you will get it. Subtract this and that, you will get it. I will just write in the next page, or may I write? Okay, I will write in the next page. We will start from here. You can see, yes, our E5 then is R times F1 minus F2. So, if we substitute these two, it will be L2 P1 minus M P2 divided by L1 L2 minus M square minus this fellow M P1 minus L1 P2 M square minus L1 L2 is equal to, just shorten it, you have, yep, you can do it, L1 L2 minus M square, this remains L2 P1 minus M P2 plus M P1 minus okay. Let's check, because I tend to make careless mistakes. So, please check. Fine. So, you have E5 and then we proceed to obtain the equations for each of these. What are the storage elements? This and this. So, we will have to do it accordingly. So, what are the state variables? Q7. So, that is the state variable related to this storage element, but though this fellow is one element, it is actually treated as two storage elements, because there are two momenta. So, P1 and P2. So, you have P1, P2. We will have to find out the equations for each of them. Let us start with this. So, there, in order to find out this Q7 dot, we ask this question, what does this element receive from the system? So, what does it receive from the system? So, F7 is equal to Q7 dot, then you bring to the side, start with F7 and then we write F7 is what? F7 is F2, F2 which is known, you just substitute it from here. Where is it? Yeah, F2 you just substitute it from here, done. So, this is M P1 minus L1 P2 divided by M square minus L1 L2. Then, so we need to ask the question now with respect to P1. P1, what does this element receive from the system through this particular bond? E1. So, E1 is equal to P1 dot is equal to, so we write E1 in this side and then we start off E1. Where does this information come from? E3 minus E4, E3 minus E4. Now, E3 is known, which is E, externally applied voltage. E4 is E5, yes, E5, and E5 is known here. So, just substitute it there, you have the equation. So, is equal to E minus R times this big stuff L2 P1 minus M P2 plus M P1 minus L1 P2 divided by L1 L2 minus, done. Third question we ask with respect to this particular bond, this element receives E2 through this bond. So, we start with E2 is equal to P2 dot is equal to E2, and E2 is E6 minus E7, E6 minus E7. Now, what is E6? E5. So, E5 minus E7, and both these are known. Okay. E5 is this and E7 is this. Substitute. So, see, the rest of the procedure is pretty simple. All you need to do conceptually is to draw the proper bond structure, that is it. So, if you draw the proper bond structure and properly represent this particular element, then everything falls without any problem. Fine. So, you have understood the issue of fields. There is one more issue I will need to cover before I can end this topic, that is, see, always we have considered the bonds that carry power, and that is true for most of the cases, but there are situations where there will be bonds that does not carry power. Example, suppose there is a circuit and you have placed a ammeter, right. The ammeter does what? It measures the current, but the ammeter itself does not consume any power, okay, because the voltage across it is 0. So, it is an observer. In the real sense, the ammeter is an observer. So, whenever we have an observer in a system, then obviously the bond to which it is connected will carry no power. You might say that what is the point of connecting the observer at all? We do it for two purposes. One, to know what it is, what the current or the voltage is, and two, for doing some kind of feedback action, because whenever we do a feedback action, we sense something and on the basis of that we do a feedback. So, that sensing is of that type, right, ammeter, voltmeter, that kind of measurement, or we measure the speed, we measure the torque, something we measure. So, we measure something, on the basis of that we put some action. So, there are two places where we would need such things. One, where we have to observe something. Now, well, you might say that here, as far as the bond graph is concerned, you after all have the state variables. So, if you solve the equations, you get the state variables, and therefore, you are already observing the state variables, true. But there are situations where you want to observe something other than the state variables. For example, what is a state variable related to a mass? Its momentum. But suppose you want to observe its position, will it be available from the equations? No. Suppose you want to observe a mass's position, and depending on that you want to control something, very possible situation in a control system. So, in that case, that particular variable, the position, will not be available. Imagine a capacitor. What is the normal state variable through it? The charge. Fine. So, now if you think that no, I want to observe the current through that capacitor, is it available in the equations? No, it is normally not available in the equation. So, if you solve the equation, you will get only the charge through the capacitor. So, in order to sense the current, that means you are laying out your model in such a way that the current will also be available as some kind of a sensed variable, on the basis of which you can do something. In that case, it will not normally be available in the existing bond graph. You have to do something in addition to it. Let us see how we can do that. But then it is clear that wherever we are observing something, it will have to be done by means of a bond. See, suppose there is a bond like this, connected to the rest of the system, say the rest of the system. And here this bond is connected to some observer. Then either it observes the flow or it observes the effort, but it cannot observe both, right. It will not observe both in the same place. So, if it observes the flow, the effort is 0, then only it carries no power. If it observes the effort, the flow is 0, then only it carries no power, which means that for a observing element, something that observes, one of the variables has to be masked, it has to be 0. Now, whenever we have this kind of a situation where we are sensing it, there we put a full arrow, meaning that this particular bond graph, particular bond will carry no power. Fine. Or you can say, in place of the rest of the system, you can also say it is a junction, because it is always connected to some kind of a junction. So, in this part, so from a junction to an observer, it has to be activated. This is called an activated bond. Now, it is clear that it could be either carrying the information of the effort, masking the information of the flow, or it could be carrying the information of the flow, masking the information of the effort. If it carries the information of the flow, we will simply write F. It could also be a bond that carries the information of the effort, we will write E, because without writing this you never know what it is observing. So, the junction here, and here is the observer. Now, if it is observing the flow in a junction, then obviously the junction has to be what kind of junction? It has to be one junction, because it has to be one junction, and the direction of the information flow would be like that, flow is going that direction. While if it is an observer connected to a junction which is taking away the information effort, effort is going in that direction, flow will be going in that direction logically, then but flow actually does not go, but nevertheless the moment you say that effort is going that direction, the causal stroke has to be given there. So, these are the activated bonds, remember the word. Let us illustrate a few situations where you need that.
So, what is the case of wattmeter when it takes both?
Wattmeter actually does not measure the current and the voltage at the same place. It measures the current through a line and the voltage between things. So, it has to be taken into account in that way. So, whenever you talk about a wattmeter, it is not really measuring the voltage as well as the current in a specific bond. No, it never does so. So, just keep that in mind. So, all that will be needed in order to do the effect of a wattmeter is to have an activated bond to measure the flow, another activated bond to measure the effort, product them. Fine. So, you have understood the concept of the activated bond. Let us come to some.
Sir, how do we determine to which junction which observer is connected? Like if it's a flow observer.
I will come to that. So, his question is, how do we know to which junction which is connected? We will see. Let us take some examples, then it will be clearer. One example can be, say, a simple mechanical system with mass, spring, damper arrangement with a cam down there with a mass. So, we know how the bond graph is. So, just let me do it fast. It will be first here an one junction connected to the SE, connected to I, which is the mass. So, this is the force, connected to here a 0, then you have the two things connected. The 0 will be connected here to the SE, SF, and here it will be connected to a one junction to the C to R. It is the other way of doing this particular bond graph that we already showed. This is already done, that is why I am not talking about the whole details once again. Normally, if you put the power directions, they will be like this, and here you could put it both ways. So, let us put it say like this. Now, causalities. Start here, done, start here, done, then the storage elements like this, like that. The moment you have done that, it is totally causal. The moment you have done that, it is not yet totally causal. So, the R, oh, these two are already done. So, these two are bringing in the flow information and taking out the effort information. Therefore, the effort has to come from here. Effort has to come from here, and if the effort has to come from here, the stroke is here. So, the flow went already in, it has to be distributed like this. Good. So, it is causal, but notice at this moment, if you solve this, if you write down the differential equations and solve them, what you have? You have here here is the k and here is the m. So, you have, let me give the numbers, say 1, 2, 3, 4, 5, 6, 7. So, what are the state variables? State variables will be P2 and other storage element is this one Q7. The momentum of this mass, which is proportional to the velocity of this mass. Therefore, in solving this, you will get the velocity signal and start from some initial condition, solve this differential equation, you will get a waveform that will represent the velocity, but not the position. Okay. So, the position is not yet observed, but suppose you want to observe the position. That means, you want to create another some dummy variable here. You want to create another dummy variable, so that there will be 3 equations, solving which you get this as well as the position. The question then is, what do you need to do in order to create that additional thing? Obviously, position is the natural variable of a capacitor. So, you need to connect a capacitor here. So, you connect a capacitor C, it is a dummy capacitor, but then this particular capacitor whatever you have connected should not affect the rest of the system, because if it does the dynamics changes. It is an observer, it is a measurement instrument. So, this bond has to be activated. It receives the flow and gives out the effort, and that is why the effort variable becomes a state variable. So, we will have it, but what does it receive actually? What actually flows through this bond? The flow. It receives the flow information and it generates the effort information. It generates the effort information means that is why it becomes a state variable q. So, you get it. So, this particular addition is the activated bond. Clear? So, why did we need it? Because we wanted to observe the position of this mass. We want to observe the position of this mass. So, in these situations we will need to do that. A whole circuit in which there is a capacitor, you want to observe the current through that capacitor. What will you do? Current is proportional to the momentum. Therefore, you want to measure the current means somehow you have to get the momentum as a state variable, but momentum is not a state variable of a capacitor. What do you have to do? You have to connect a dummy inductor through an activated bond. The moment you do that, it will generate the variable, necessary variable. Is the question clear now? Fine. So, the other situation that can often arise is where this particular thing, that means the position sense, is used to do some control. Let us illustrate one situation. Suppose we consider the whatever we did earlier. You have got a mass, a spring damper arrangement, as we have many times considered this. There is a force and there is another mass, but now notice, suppose that this mass, its position is being observed, and not only that, depending on the observation of this position, suppose you are controlling this force. Earlier we considered that this is a externally applied independent force, but now imagine that it is a control system, you are observing this particular mass's position, and then you are, I will do that by a dashed line, you are controlling it. Obviously, when you are measuring the position and you are controlling the force, here at this point, what is available? A flow variable. At this point, a flow variable available. This flow is being sensed, and therefore, it has one unit. When it gets turned into a force, it has completely different unit. So, there has to be some kind of a multiplying factor, which I will represent by means of a sort of a gain, some gain block. Say the gain is alpha. Good. Now, how do we represent this? The rest of the thing is already known to you, that is why I chose this system. So, that the additional incremental thing that we did, that is what we try to understand, the rest of the things is known. So, first let us quickly draw the bond graph. Let us draw the bond graph here. You have got a one junction here, one connected to, we have already some other did this. We do not need to do this in a very longish way. We have already seen that this will be simply C, this will be simply R, right, and then this fellow will be your, mass will have to be connected. So, I, then it will be connected to the transformer will be connected to this one. So, it will be 0 to the C 2 to the mass connected by one junction to the I element. Okay. That is the normal thing, and we said that this one junction would not be necessary because you can do it through, but we will not do it now that way because we need this sense here. At this point the flow is available. So, we are measuring the flow. So, what we will do is we will put a bond starting from here going all the way, but then here is a flow variable, and when it gets inputted here, what is it? An effort, it is force. So, in between you have to connect a gyrator. So, there has to be a gyrator in between. So, what are we doing? We are observing the flow here and we are applying an effort here. So, it is a feedback control system. So, that has to be represented by this, but then the moment you observe the flow, then it is an observer, and therefore, this has to be masked. And what is going through is flow, and the other one is not going through. If it went through, then it would give a back force on this, so which we do not want. So, it is not giving any, it is taking the flow, but it is not giving the effort. So, it is done, right. So, now let us put the power directions. Here the power comes, and naturally we will say the power goes. This is obviously not carrying power, but the power direction is still meaningful because that sets the positivity and the negativity here. Now, let us give the causalities. The causality of this one is integral causality is like this. Flow has already come into this one junction, it must take out the flow in all the directions. It is a transformer, so it must transfer the flow. It is a zero junction, so let us put the causality of the C element this. The moment to do that, if information of the effort has come into the zero junction, it must distribute like this. At this point it is not yet determined, so let us put the normal causality of the I element. It gives the flow, receives the effort. The moment it is given the flow, this one junction is completely determined, so it must take out the flow information. Notice that the gyrator's proper causality is done. So, this is where the flow is going in and this is where the effort is going out. One more important thing to consider is that even though this particular bond is not carrying power, this particular bond is carrying power because it is applying the force. So, in this case this is not power conserving, that you have to keep in mind. Fine. Let us obtain the differential equations of this.
Sir, in this case, when we are putting this observer which is giving the flow information, can't we just blindly put the causality stroke here? Because
here?
Yes.
It is after all taking the flow information. Yes, you can do that. So, his question is, can't we blindly put the causal stroke here? Yes, you can do that. Because if you are trying to observe the flow, it must be connected to a bond where the flow information is already available, and that happens in a one junction. So, it is already there. Okay, now let us number them 1, 2, 3, 4, 5, 6, 7, 8, 9, C 10. There are many things. Let me, if I have to do this here in this page, it will be difficult. So, let me just in short draw the diagram, otherwise you will not be able to follow. So, it is a 1 connected to a C, connected to a R, connected to transformer, connected to 0, connected to C, connected to 1, connected to I, and then from here it gets through a gyrator to this. Oh, there is an inductor I. So, done. I will have this, C will be this, R will be this. All the causalities put? Yes. Let me, activated, oh, activation, yes. I'll give the numbers in another color, so that otherwise it will be too jumbled. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Okay, all of them done. So, now let us start asking the first question. First question is, what do the elements give to the system? So, the first, this is bond 1, what does it give to the system? Flow 1. So, let me say F1 is equal to what? P1 by M1. This is M1, this is M2, this is K1, this is K2, this is R, this is A, B. So, the transformer ratio is minus B by A, and the gyrator ratio is alpha. So, F1 is done. Then C, what does it give to the system? E2, E2 is Q2 by C. Oh, sorry, KQ2. It is a mechanical thing. K1, Q2. Sorry. Then the R element. Better let us first complete the easier things. The capacitor, this spring. That will be E7, which is Q7 K2, right? And this one is F8 is P8 by M2. Fine. So, we have obtained the ones related to the storage elements. Now, let us start asking the question to this particular element. So, it is giving what? It is giving effort. So, E3 is RF3, and then RF3 comes from, yes, RF1, and F1 is known, RP1 by M1. E3 is done. So, what is remaining? This and that. What does the transformer give through this bond to the rest of the system? It gives effort. So, E4 is equal to minus B by A times E5. E5 comes from E7, right? 0 junction, E5 is equal to E7. So, minus B by A E7, which is Q7 K2, done. Then it gives in this bond, what does it give? F5, F5, that will be related to F4. So, it is minus B by A F4. Now, what does F4 come from? F1, fine. So, minus B by A F1 is equal to minus B by A P1 by what else remains? Gyrator. What does it give to the system? E10. So, E10 is equal to, it is related to something here, alpha F9, right, it comes from here, is equal to alpha F8 is equal to alpha P8 by M2. Done? What does it give to this side? Nothing. Yes, nothing, because it receives a flow here, but it gives nothing to this side. So, we will not ask this question to this bond. That is the speciality of the activated bond. So, when we ask the question what do the elements give to the system, we will ask this, we will answer this question related to this side of the gyrator, but not to this side, because this side is activated. So, all these things are done. Then comes the next question, what do the integrally causal storage elements receive from the system? So, that is, what are the state variables? P1, Q7 and P8, right. So, these are the storage elements, this and this, huh? Yeah, Q2, sorry, Q2. There are 4 storage elements. So, let us ask this question to each one. P1, what does it receive from the system? E1, E1 is equal to P1 dot is equal to E1, and this fellow comes from, E1 comes from as a summation of all this. So, we will write it as a summation. Notice now we have to do the power derivations correctly. E10 minus E2 minus E3 minus E4, right. So, E10 minus E2 minus E3 minus E4. Okay. Now, all these are probably known, just check. E10 is known, fine. So, E10 is known, E2 is known, E3 is known, E4 is known, just substitute. Good. Next question. Let us ask with respect to Q2. What does it receive from the system? F2. F2 is equal to Q2 dot is equal to F2. Then F2, where does it come from? F1. So, F1, which is known, P1 by M1, right. So, you substitute it here. Then we ask the question Q7. So, it is F7, it receives F7 is equal to Q7 dot is equal to F7. Where does this information come from? F7? F5 minus F6, right, it is a 0 junction. So, the flows are summed. So, F5 minus F6, F5 minus F6. Now, F5 happens to be available, F6 happens to be, no, we have to find out where it comes from. F6 comes from F8, yeah, is equal to F5 minus F8, both these are known, fine. So, now finally, we have to come to 8. So, what does it receive from the system? E8, E8 is equal to P8 dot is equal to E8, E8 comes from, notice E6 only, because it does not give. So, it is E6 only. These are the things you have to remember, E6 only, not E9, because it does not give the effort here, E6 only. E6 is E7 and E7 is known, put it there. Okay. So, all that you have to do or remember while dealing with activated bonds is this: here one of the variables is 0, rest of the things are simple. Fine. So, we will continue in the next class. Let us end here.